Okay, thank you. So in this lecture, what I want to do is try and sketch the main ideas that go into the proof of this Feng-Yun Zhang arithmetic Ziegel-Wey formula that generalizes the arithmetic Ziegel-Wey formula from the number field case to the function field case. So just recall the basic setup. Just recall we're working with a fixed finite tall double cover, x prime to x, of smooth projective geometrically connected curves. Over some finite field. Um, and sigma is the non-trivial deck transformation. Now we fix some integer n at least one, and recall the smooth n r dimensional k stack, the moduli space of un Shtukas with r legs. So I won't remind you of the definition, but we have this. So if you look at Hermitian vector bundles of rank up to r on the curve, for every fixed rank d, we constructed special cycles in codimension r times d. So we're mostly interested today, maybe entirely interested today, in the case where d equals n, so that we actually get 0 cycles. So today, we'll only look at rank n Hermitian vector bundles EA on x prime. And not only do we only want the rank n ones, this Feng-Yun Zhang theorem was only a statement about the non-degenerate ones. Only look at rank n Hermitian vectors and that are non-degenerate, which meant that the Hermitian pairing was generically an isomorphism, or equivalently, this is injective. Okay. So then, for such an EA, we have the special 0 cycle. So there were these fancy corrected cycle classes, but in this that we constructed some naive class and then hit it with some copies of somehow r different tautological bundles on the curve to correct the codimension. But in this non-degenerate case, there's no correction. The naive thing is the thing that we are already interested in. And then the theorem that we're trying to prove, so the goal is the following theorem. Let me move down. The goal theorem of Feng-Yun and Zhang is that the degree of any one of these non-degenerate special 0 cycles is the rth derivative at s equals 0 of the EA Fourier coefficient of some Eisenstein series for an unramified Eisenstein series EHS on the quasi-split unitary group UNN over the field of rational functions of the ground curve. Okay, so let's give it a try. So the first thing we want to do is absolutely positively not fix one pair EA. We really want to treat all of them, at least all the non-degenerate ones, on equal footing. So we're going to define a moduli space of all possible EA. Moduli space over K. All EA. So I'll tell you exactly what's K. We're only in the end interested in the Hermitian vector bundles EA that are really defined over the curve X prime. But when we form this moduli space, we want to allow the possibility of base changing X prime to any K algebra. And so I'll tell you what the coefficients are. The points of the moduli space of coefficients are over the algebraic closure. Over the algebraic closure, we're just looking at rank n, non-degenerate. Non-degenerate. Hermitian vector bundles EA, well, after I take my curve and base change it to the algebraic closure. So those are the k-bar points of the moduli space. And we have a function that we're interested in understanding. A function only on the k points. And the function is, it takes a k point, an EA, and sends it to the degree of the corresponding special zero cycle. Okay, so the first idea is if you have some, so I mean, in what sense, by the way, does this moduli space exist? It exists as an Artin stack, which is fine. It's close enough to a scheme to make everything work. So Grothendieck tells us that if you have some variety over K and a function just on its K points, you should try to sheafify it in the following sense. So Grothendieck's sheaf to function dictionary says any, so constructible L-adic sheaf L on our K stack A determines a function on the K points valued in QL. Just fix forever some auxiliary prime L that's prime to the characteristic of our ground field K. Sending the point X to, well, if I take my sheaf and I take its stalk at some geometric point above X, I get a finite dimensional QL vector space with some Frobenius operator on it. And so then you can take the trace of Frobenius on the stalk at that point X, and it gives you an element of QL. So sending the point X to the trace of Frobenius on the stalk Lx at some geometric point stalk at some geometric point above X. So in other words, x goes to the trace of Frobenius. And then you can extend this, so there's an obvious extension. So instead of just a sheaf, I can take, well, I'm still going to call it a sheaf, but an L in D of A, which is the bounded derived category of constructible L-adic sheaves. So instead of just taking a sheaf and turning it into a function, you can take a complex of sheaves and turn it into a function. And so the obvious question is, can we find some sheaf such that when you apply growth and decay sheaf to function dictionary, it recovers this function that we're interested in, the one that counts points in our zero cycle? So can we find some sheaf such that point by point we get the thing that we want? And the answer is no, but almost. It's a little bit more subtle than that. So instead, this is what we're going to construct. Instead, there's going to be a sheaf, and it's going to be endowed with some sort of endomorphism, something like a Hecke operator. That I'll call T from L to L, such that you don't quite get you don't get the degree of the zero cycle by taking the trace of Frobenius. What you do is this magical endomorphism, this T, is supposed to, in some literal sense, add legs to the Shtuka. So if you take the trace of Frobenius composed with T r times and apply that operator to the stalk at EA, that's going to give us the degree of the zero cycle. So this is the first key idea. And I'm going to tell you how to construct this sheaf and this operator. And the way to understand how this works is to first just focus on the case where r equals 0. Now, when r is 0, what does our zero cycle look like? So it's something very explicit. Our Shtukas have no legs, and so we're really just talking about Hermitian vector bundles on X prime. So in the case of 0 legs, what are the k-bar points of our special cycle? Well, they are just isometric embeddings E into F, where F is a self-dual Hermitian vector bundle on X prime, no base change to k-bar, of rank n, the same rank as E. So we're just counting the number of ways to start from E, which is already non-degenerate, and just enlarge it to something self-dual. Okay, so the Hitchin fibration. M to A, F. So everything on the geometric side of the Siegel-Wave formula is going to come down to understanding the structure of the following map of K-stacks. where the k-bar points are, well, okay, I have told you what A is. So that's just the non-degenerate rank n e a on x prime base change to k bar. And a point of M is, okay, so one of those things. Plus a rank n self-dual f on x prime with an isometric embedding. Now, okay, what's the point here? So if I fix a k point downstairs and look at the fiber upstairs, the fiber M sub E A is a k stack such that, okay, I mean, just by definition of the moduli problem, to give a point, a k point of the Hitchin stack in the fiber of EA is to give a self-dual f of rank n on x prime, no base change, with a map, an isometric embedding of E into it. Right? That's just a k point of the thing I wrote down. But the point is, that's the same thing as a k bar point of our zero cycle. So the k points of the Hitchin stack M are the same as the k bar points of the zero cycle we're interested in. So, I mean, what have we actually done? What have we achieved? We started out with a zero-dimensional stack over k, and we found a higher dimensional stack over k, such that the k bar points of the zero-dimensional guy are the same as the k points of the higher dimensional guy. We've taken the k bar points of one stack and realized them as the k points of another. Why? What is the point of doing that? The point of doing that is that we have tools for counting the k points of a stack or a scheme, like the Grothendieck-Lefschetz trace formula. So by the Grothendieck-Lefschetz trace formula, if we want to count the k bar points on our special cycle, that's the same as counting the k points in this Hitchin fiber, which is the alternating sum of the trace of the Frobenius operator on the cohomology of the Hitchin fiber. Okay. Where my cohomology has coefficients in QL, and I'm being sloppy because this Hitchin fiber is a k-stack, but when I take cohomology, I mean the cohomology after you base change to k-bar. Okay, but the cohomology of the Hitchin fiber, it comes from a sheaf. So this is, you take the ith higher direct image of the constant sheaf upstairs on the Hitchin stack, and then you take its stalk at EA. So the cohomology is interpolated into a sheaf. So what we've done is express now the number of points on our zero cycle over the algebraic closure as the sum of the trace of Frobenius on the stalk at EA of the higher direct image. And then that's the same as if you think of all of the higher direct images as I varies as coming from just some one object in the derived category, then there is no sum anymore. This is the trace of Frobenius on the higher direct image. Take the stalk at EA. So this is an object in the derived category. So that's great. At least for zero legs, we've successfully done what Grothendieck says we should do. We have found a sheaf such that when you apply the sheaf function dictionary to get a function, it counts the degree of our zero cycle. And so now I have to tell you how to upgrade this, endow it with an operator T that's going to add legs. Okay, so now we want to construct this T. Okay, so like I said, this T is the thing that adds that's going to start with a zero Shtuka and add legs to it, one leg at a time. So it should be plausible that the following construction should work. So the Hecke stack, HK over spec K. Again, I'll tell you what the K bar points are. Okay, so a K bar point of the Hecke stack is going to be the following list of data. So there's going to be a point, one of these EAs, on the base of the Hitchin fibration. And then we're going to take two self-dual Hermitian vector bundles related by a simple modification and a map from E into both of them. Plus self-dual rank n Hermitian vector bundles F0 and F1 on the curve, base change to K bar, and a point, a geometric point of the curve, and a diagram. So I'm going to take this E and I'm going to map it into both F0 and F1. And I want F0 and F1 to be related by a simple modification at the point X. So that's the data of the Hecke stack. And just it's constructed so that this Hecke stack, okay, I mean, it admits a map to A, just remembering the first bit of information. But if I take the EA and just remember the map from E into F0, well, that's a point of the Hitchin stack M. Or I could just remember E and its map to F1. And that would give me another map to the Hitchin stack. And so I get this picture. So it looks like a Hecke correspondence, hence the name. And I claim this, just the existence of this stack, this defines the endomorphism of this higher direct image that we're looking for. So this already defines the endomorphism, an endomorphism. And how is that? Okay, I mean, it's a bunch of cohomological nonsense. I'm not going to tell you the whole construction of the endomorphism, but I'm going to describe what it is fiber by fiber. So consider, so how? All right, consider the action on the fiber at some point of the Hitchin base. Take a k-bar point. Okay? If I take this picture and I take this point downstairs on A and just take the fiber above it on everybody, I get the following diagram. So downstairs, I replace A by just this one point, spec K, and then I have the Hitchin fiber, and the Hitchin fiber again, and then the fiber of the Hecke stack, and maps. Okay. Now, I'm trying to construct an endomorphism on the level of fibers. Well, if I take the fiber of the ith higher direct image, that is the cohomology of the Hitchin fiber. Okay? But if I have a cohomology class here, I can pull it back by the first arrow, P0, to the cohomology class on the Hecke stack, which then I can push forward by the other arrow. So these two guys here, same dimension. So I push forward and I end up in the same cohomological degree. But again, that's just the stalk of the higher direct image. And that's telling me what T is on that fiber, that stalk. And so, I mean, you should find it plausible that getting from this stalk by stalk description of T to actually getting an endomorphism on the level of objects in the derived category is just kind of a bunch of formal hoo-ha. This is what T is. Okay. So this has the property that we want. I mean, I'm not going to prove it, but this sheaf with this endomorphism, if you take the trace of Frobenius with this endomorphism iterated r times on a stalk, you get the degree of the zero cycle. But what are you supposed to do with that? So now you need to really understand what this sheaf, this higher direct image, is in some meaningful sense, and what this endomorphism is doing to it in some meaningful sense. You need some sort of concrete way of understanding this. So we need to understand this operator T in much greater detail. Okay, so first of all, this A, this Hitchin base, is some like extremely big thing. It's not a finite type. So we want to break it apart into somehow more manageable open and closed substacks. So if I take any point in the Hitchin base, I can look at sort of the failure of the Hermitian form to be self-dual, and that's sort of obviously measured by the co-kernel of the Hermitian map A that encodes the Hermitian pairing. Now, because we're assuming that A is injective, this co-kernel is going to be very small. It's going to be a torsion coherent sheaf on X prime, which means it's supported at finitely many points. So it has a support divisor. Which means the obvious thing. It's a divisor on X prime whose the support divisor is you just take the points in the support of this co-kernel, but you give them some multiplicities depending on the length of the stalk of this co-kernel at that point. And then you can decompose the Hitchin base A by looking at points where the support divisor has a particular degree. This divisor has even degree, and it's not hard to see that it's fixed by the deck transformation. So we get a decomposition into open and closed substacks. A is going to be the disjoint union over D greater than or equal to 0 of AD, where this is the locus of pairs. So it's those EA for which this co-kernel has degree 2D, support divisor. So as you look at points of AD with D getting bigger and bigger and bigger, your EA is getting farther and farther away from being self-dual. If you were on A0, those would be the self-dual guys. Okay. Now, for reasons that will become clear in a moment, I want to do the following. I want to construct, over A, we've got this Hitchin space M. And I want to construct something above M, something more complicated. That's going to be called AD tilde. That'll map down to, so now I'm going to fix one of these ADs appearing in this decomposition and just work on that. And so I take, in the Hitchin space M, I just take the pre-image of AD and call that MD. So we still have a Hitchin map. And now I'm going to construct an AD tilde above that. Well, okay, this AD was, so again, K points, K bar points. This was an EA on X prime K bar. Points of the Hitchin stack above it. So there was an EA and an embedding of E into F, where this guy is self-dual. But then I can, if I have an embedding of my non-degenerate guy into a self-dual guy, I can ask, okay, how did I get to the self-dual guy? I started with my E and I enlarged it to something that was self-dual, but I could enlarge it a tiny bit and then a tiny bit more 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 until I eventually arrive at something self-dual. So let's look at all the ways of starting from EA and enlarging it a tiny bit at a time until you hit self-dual. So an EA and a complete flag starting from E, which I'll call F0, I enlarge it a tiny bit to some F1, and then enlarge it a tiny bit more to some F2, and keep going until I eventually hit something self-dual. And by complete flag, I mean that at each step, I enlarged it as small as I possibly could. So that means that each Fi mod Fi minus 1 is a skyscraper sheaf. X prime k bar. Complete flag of Hermitian vector bundles on X prime k bar. Okay. This looks pretty complicated, and it is pretty complicated. If you start out with an arbitrary point downstairs on the Hitchin base, the fibers of both of these maps over this point are extremely complicated. They can have varying dimensions. They're kind of almost impossible to understand directly. But there's an open, dense subset of AD over which this whole picture becomes really, really simple. So, I mean, somehow the fibers of these maps are complicated. You can imagine that I had a point EA um, where this co-kernel sheaf had sort of very high degree, but was supported at a single point. And when that happens, there's somehow lots and lots and lots of ways to construct these flags. But at the other extreme, you can imagine that this skyscraper sheaf, that this co-kernel is extremely spread out. I mean, it's 2D distinct points and just a little tiny one-dimensional skyscraper sheaf at each point. And in that case, that's where these fibers are much easier to understand. So let AD circ inside of AD be the regular semi-simple locus pairs for which this co-kernel sheaf has multiplicity-free support. i.e. is a direct sum of skyscraper sheaves at 2D distinct points. Of X prime. And I claim over this regular semi-simple locus, we can understand very explicitly what this Hitchin space M is and this AD tilde above it. So here's the picture. I've got AD circ sitting inside of AD. So this is open and dense. I've got the Hitchin space above it, this strange AD tilde above it. And then I can take the pre-image of the regular semi-simple locus in the Hitchin space and in this AD tilde. And then all of the horizontal arrows are open and dense. Okay, so here's the reason for introducing this AD tilde in the first place. Here's a lemma. Over the regular semi-simple locus, if I look at this AD0 tilde mapping to AD circ, this is a finite Vital Galois cover. With Galois group, what I'll call WD, and it's the symmetric group on D elements, semi-direct product, D copies of plus or minus 1, which is pretty easy to understand. That's a perfectly nice, reasonable group. So here's the idea of the proof. Fix a point. Downstairs. What does it mean to give a point of this AD tilde above it? Well, a point of AD tilde circ K bar above it is a complete flag E0, F0, F1. You keep enlarging it until you get to some self-dual guy. But if that's self-dual, so now I can take this flag and I can kind of dualize the whole thing. If this is self-dual, then FD is the same as sigma pullback FD check. And then the inclusion of FD minus 1 into FD gives me an inclusion of this into sigma pullback FD minus 1 check, all the way down to sigma pullback F0 check, which is sigma pullback E check. So my length D flag actually extends in a natural way to a length 2D flag of things all between E and sigma pullback E dual. And each inclusion is something really small. So meaning each quotient is just a skyscraper sheaf supported at one's point. So let's let x1 be the support of f1 mod f0. Let x2 be the support of f2 mod f1 all the way down to xd. And then what happens if you keep on going? Well, if you take the next co-kernel, you'll get something that is in fact the sigma conjugate of the previous point. So this will be the support of sigma pullback fd minus 1 check mod sigma pullback fd check, all the way down until you get back to sigma of x1. So what is this saying? It's saying that once I fix a point downstairs on the Hitchin base in the regular semi-simple locus, to give a point above it is to give this flag, but in fact, this flag is completely determined by saying what the supports of these co-kernels are, because I just have to tell you, okay, you enlarge it at this point, and this point, and this point, and do it in this order. So a point of this AD tilde above EA is, let's say, to give a point. Well, a point is an ordering of the points in the support of this little tiny torsion sheaf, but not an arbitrary ordering of the points. It's required that when you order them, you list D of the points, but in those list of first D things, no point is ever conjugate to any other point. And then you list all the conjugates. But if you think about it for a second, the set of all possible ways of ordering the points in the support in this way has a natural action of WD. So the set of all such orderings is a simply transitive WD set, where the symmetric group acts just by reordering x1 through xd, and then when you reorder those, you just simultaneously reorder these appropriately to keep the shape of the ordering to retain this sort of mirror symmetry that it has. But then the plus or minus 1 to the d acts by, well, there's a transposition that just replaces, it swaps x1 with its conjugate in the list. So I would move this guy to the beginning and move this guy to the end and leave everybody else fixed. Or I could interchange the roles of x2 and sigma of x2 and leave everybody else fixed. And that's how this plus or minus 1 to the d acts. And that's essentially why this lemma is true. But it's important to do to make this argument. It's important that the x1 through xd and their conjugates are really d different points. Okay, so what does this buy us? So now, if you think about this for a few minutes, it's pretty easy to see under the Galois correspondence, so we don't really care about this AD tilde. What we really care about is the Hitchin stack. But that's some intermediate cover inside of this Galois extension, so it corresponds to some subgroup. And from the explicit description of the group of deck transformations of this Galois cover, it corresponds to the subgroup, the symmetric group inside of WD. So this top guy is a Galois cover with group, the symmetric group. Okay? But that's a pretty good explicit understanding of what this Hitchin stack looks like, at least over this open dense subset of the base AD. And now the magic starts to happen. So in particular, the fact that we have constructed this cover of AD circ with Galois group, the group WD, what does that do? Well, it gives us, it realizes this finite group as a quotient of the Étale fundamental group of AD circ. Okay? Which means we get a functor from representations of WD on finite dimensional QL vector spaces. Well, any representation of this group WD, we can now pull back to a representation of the Étale fundamental group. But representations of the Étale fundamental group are the same as L-adic local systems. AD circ. aka least L-adic sheaves. So we've got a machine that eats representations of this perfectly nice finite group and spits out sheaves on this open dense subset of this one open and closed substack of the Hitchin base. And so what are we trying to understand? Remember, we're trying to understand, oh, it was a while ago, we're trying to understand this, this sheaf, the higher direct image of the constant sheaf under the Hitchin map. Okay? So that, okay, that's some sheaf. If I restrict it to the regular semi-simple locus, I get some sheaf here. When I restrict it to the regular semi-simple locus, the fact that this is a finite Étale cover means I'm actually getting a local system, just viewed as a complex in degree 1 in the derived category, and it is in the image of this functor. And the fact that this dense open subset of the Hitchin stack corresponds to this particular subgroup is telling me what the corresponding representation is. You take the trivial representation and you induce it from SD to WD. So you take that finite dimensional representation, you apply this machine to get a sheaf, and that's the higher direct image of the Hitchin map restricted to the regular semi-simple locus. So we understand this guy very well. But that's not good enough. We need to understand this higher direct image over all of AD, not just over this open dense subset. And this is where the voodoo happens. So now you invoke the theory of perverse sheaves. So we already have this functor, representations of WD to local systems on the regular semi-simple locus. So I'm going to give that a name now. I'm going to call it rho goes to bracket rho. The theory of perverse sheaves says, so this regular semi-simple locus is not just open and dense in AD, it's also smooth. And so there's this magical functor called IC extension, which takes a local system on a smooth, dense open subset and produces a perverse sheaf on AD, and those live inside the derived category of L-adic sheaves. So there's some canonical way of taking a local system and extend a local system on the regular semi-simple locus and extending it to some sheaf on the whole space. A black box. But then the proposition is that if I want to get the higher direct image of the constant sheaf, under the Hitchin map, what I do is I can restrict it back to the regular semi-simple locus and then apply this extension. But I've just told you what the higher direct image is over the regular semi-simple locus. It's the thing that you get when you apply this functor over here to this nice, very pleasant representation. And so this first property, the fact that this higher direct image is completely determined by its restriction to this dense open subset, if you know about perverse sheaves already, then you know that the property that you want is for this guy to be a small map in the technical sense. And if this is a small map, then this first property is true. And it is a small map. And I mean, if you haven't seen anything about perverse sheaves, what is a small map? Okay, it means it's going to be generically finite, which it is. Generically, we've seen that this is a finite Étale cover. But it's allowed to have some fibers of higher dimension, but the locus on the base, where the fiber has high dimension, has low dimension. So it's allowed to have high dimensional fibers, but not very often. And the notion of small is just some precise bounds on these dimensions that's constructed, that the definition is cooked up precisely to make this property true. And the fact that this is a small map is really, it follows from a theorem of Le Mans. It's the smallness of the Hermitian analog of the Grothendieck-Springer resolution. So the smallness is kind of, it's kind of a miracle. And it allows us to show that this higher direct image that somehow controls the degrees of the zero cycles is completely controlled by this one little representation. Okay. So we need to understand this finite dimensional representation of WD. So for each I between 0 and D, I'm going to define a representation of WD. So this induced representation is not irreducible. So what do its irreducible constituents look like? Well, I'm going to define a character called chi from Wi, which is Si, semi-direct product, plus or minus 1 I times B trivial on Si. And then on the other factor, just multiply all the coordinates together. Now, I can think of Wi cross Wd minus I as a subgroup of Wd. And I'm going to define rho I to be you induce from this subgroup this character. Well, I mean, rather this character on the first factor and the trivial character on the second factor. Induce that up, you get some representation of WD. Okay, the next proposition. Everything is due to Feng Yun Zhang, by the way, all of this. First of all, okay, the first one won't impress you, but it's important. This induced representation, when you induce the trivial representation from SD, so this is the one of relevance to us because it's somehow the thing that's controlling the higher direct image of the Hitchin map. This is the direct sum of these rho i's. Exercise in finite groups. But the point is, this decomposition of the representation now induces a decomposition of the higher direct image of the constant sheaf under the Hitchin map, which has this Hecke operator acting on it. Okay. So what they prove is that this Hecke operator T on so this is just over this one part of our Hitchin base, the D part. Okay, on this sheaf, which you get by starting from the trivial representation of the symmetric group, inducing it up to WD, regarding that as a local system on the regular semi-simple locus, and my battery is running low. Why is that happening? There we go. We're good. Um, and then applying this mysterious IC extension functor, this sheaf now decomposes according to the decomposition of the representation. So IC bracket rho I. And this operator T respects the decomposition, and it acts as multiplication by minus I on this summand. So we've got modulo this mysterious IC functor, we've got a concrete description of this sheaf and a concrete description of the Hecke operator acting on it. And to check this, to check that this is how this Hecke operator acts, you can verify this only after restricting to the regular semi-simple locus. It's enough to prove it there. And there, it amounts to sitting down and explicitly working out the geometry of this Hecke stack. But once you know this, you get something like an explicit formula for the degree of the zero cycle. So fix an EA on the D part of the Hitchin base. So the degree of this zero cycle, so it's the trace of Frobenius composed with R copies of the endomorphism T acting on the higher direct image of the constant sheaf under the Hitchin map, which we have decomposed into a sum of subsheaves. So we take their stalks at EA and look at the trace of Frobenius and R iterates of T on that stalk. And I've just told you how the operator T acts on each one of those things. So you get the sum from I equals 0 to D of minus I to the R. That's from this statement up here, times the trace of Frobenius on the stalk of this sheaf. Okay. And that's the final formula on the geometric side, on the side of the special cycles. And that's the thing, this last expression is the one that we want to compare with something coming from an Eisenstein series. I'll pause for a moment to let you digest that. I think this is astonishing. Maybe questions? Now is a good time to ask, because now we're going to switch hard to the automorphic side. To me, this was the most fun part of the lecture series. Okay, then let's move on to coefficients of Eisenstein series. So first, let me say exactly what Eisenstein series it is. I've never told you exactly what Eisenstein series appears in their arithmetic Ziegel-Wey formula. So let me do that. So we have our fields of rational functions. And we're going to let H be the quasi-split unitary group. So a reductive group over F. And I described all this last time. It's got a Ziegel parabolic. with a Levy decomposition. And I explained how the Levy factor, its adelic points, we're identifying with GLD, where D is M. Of the adels of the function field of the double cover. Okay. So if I take the adelic points of my Siegel parabolic, so the unipotent radical n is normal. And when I take the quotient, I get the Levy factor, which I'm identifying with GLN. And then you take the determinant. And then on the adels of f prime, we've got the usual absolute value. And so this composition, I'm just going to call absolute value. Okay. And then you just do the usual thing. For any complex parameter S, you can form the principal series representation. I of S. So I induce from the Siegel parabolic up to the whole group. This character to the S plus n over 2, where the shift is chosen so that the Eisenstein series that I get has a functional equation in S goes to minus S, as opposed to shifted to somewhere else. This is an unramified representation of H, and so it has up to scaling a unique spherical vector. It has unique K fixed vector, where K was the maximal compact open in the adelic points of our unitary group. K fixed vector that I'll call phi S, normalized by demanding that it's a function on H, and I demand that it be 1 for all elements in our compact open. And so you do the usual thing. This determines an Eisenstein series by EHS is the sum over gamma of left translates of this section. So that's the Eisenstein series. So I'm rapidly running out of time, but okay, how are you supposed to understand this? So when Feng Yun and Zhang do this, they don't in some sense say anything new about Fourier coefficients of Eisenstein series. They just somehow present them in a very different way, but they're starting from known formulas. So for any non-degenerate Hermitian vector bundle, what does the EA coefficient of this Eisenstein series look like? Well, there's a polynomial that comes from Siegel's theory of local representation densities, which is a whole other mini course. But there is some polynomial with coefficients in Z such that the EA coefficient of the Eisenstein series is you take this density polynomial and you evaluate it q to the minus 2s. Now, I have a slide to show you, and so but there are explicit formulas for these, but they're extraordinarily complicated. And if there's 1 or 2 minutes at the end, I will show you a slide that gives you the precise definition of this density polynomial. It's explicit but horrible formula. But what can you do with this? So what Fengyun and Zhang prove is from these explicit formulas, so explicit formulas for this polynomial. I mean, these polynomials have been around since the time of Siegel, essentially. But the relevant formulas are much more recent due to Chow and Yamauchi. And using these explicit formulas, Fengyun and Zhang prove the following. For any EA, this density polynomial, you can think of the coefficients of the polynomial as functions of the pair EA, and then ask for corresponding sheaves in the sense of growth into Schiefte function dictionary. You could try to sheafify each coefficient individually. And that's what they did. Here is, in some sense, an explicit formula, although you should take that with a big grain of salt. This polynomial corresponding to EA is, well, you take the trace of Frobenius acting on this sheaf that comes from this representation rho I of WD that I defined earlier. That's it. These representations, rho I of WD, determine sheaves. You take the trace of Frobenius on their stalks, and you get the coefficients of these polynomials that encode the Eisenstein series coefficients. Now, this isn't an explicit formula in any meaningful sense because this IC extension functor is so mysterious. You don't really compute it in any real sense. But once you have this, you're done. So finally, you just compare these formulas. Remember, we've got the degree of our special cycle. I've explained that you can realize that in terms of the trace of Frobenius acting on some sheaves. Okay. On the other hand, the coefficient of the Eisenstein series is given by this density polynomial. And the density polynomial is given by the same sheaves. So again, because of this mysterious IC extension functor, these formulas are not in any meaningful sense explicit, but you can certainly compare them. And so by comparing these two formulas, you get exactly what you want. You just, in this formula for the Eisenstein series coefficient, you can take as many derivatives as you want. And you end up with the formula for the degree of the zero cycle. I mean, up to, there's a 2 up here in the exponent. So it's, of course, up to some 2's and some log q's that pop out when you take the derivative. And so that's it. That's how they prove their result. By my clock, I have 1 minute. And I want to use that. I mean, this proposition is one of the most difficult parts in their paper. Is one of the most technical parts. And I mean, to make it slightly less of a black box, I'm going to show you a slide that has the formula for these polynomials on it. Let's see here. Show Yamauchi. Okay. So whatever this polynomial is, it admits a product factorization over all the places of the function field f. In other words, over the closed points of our curve x. And so I'm going to tell you what the local factors are. So at any place of the curve, you can look at the completed local ring of x and the completed local ring of the curve x prime above it. And you can take this Hermitian lattice, take this Hermitian vector bundle and take its completed stalk. And what you get is a Hermitian lattice over this complete local ring. And then this density polynomial is going to factor as a product of polynomials over all the places. And each local polynomial only depends on this local Hermitian lattice for a complete local ring. And here it is. Here's the formula. Okay. So the important thing maybe is the summation. So you look at all lattices, you look at all ways of starting with your local Hermitian lattice determined by the vector bundle, and you look at all ways of enlarging it, not to something self-dual, but to something that's contained in its own self-dual, its own dual lattice. In other words, the sum is over all ways of enlarging your lattice to something on which the Hermitian form remains integral valued. And you run over all these possible lattices, and then it's t, and then, okay, there's some number associated to this lattice I, that's down here. And then there's some other number associated to this lattice, and that's down here. And then there's some explicit polynomial where the eta v is plus or minus 1, depending on whether v is split or inert, and qv is the residue degree of this place. So this is the formula. From the point of view of the proof of Feng Yun and Zhang, you might as well take this as essentially the definition of the Fourier coefficients of the Eisenstein series. And starting from this, they systematically find corresponding sheaves that will give rise under Grothendieck's dictionary to the coefficients of this polynomial, which is a very complicated and tedious process. But in the end, all of the sheaves that they construct are, I mean, they're of a geometric nature, and they lie between this AD and AD tilde. And any sheaf that you construct using geometry of schemes that lie between AD and AD tilde eventually will lie in the image of this functor that takes representations of the finite group to sheaves. And so they work out what these representations of WD are. And after a long and painful process, prove that they just are these same rho i's that appeared in the formula for the degree of the zero cycle. Okay, so that's it for this morning. And tomorrow in my last lecture, I will talk about the theorem that I stated last time that extends this arithmetic Ziegel-Wey formula to pairs EA, which instead of being non-degenerate, are allowed to be just a little bit degenerate. But I'll stop here for today. Thank you.
Thank you. Yeah, are there questions, comments?
Just a vague question. Did the Hitchin vibration appear on the previous work on the gross Zagi, for example?
Yeah, there's an analog of it in the Yun and Zhang proof of the higher derivative Gross-Zagier formula. Yeah, absolutely.
Is there any motivation of Hitchin vibration suddenly coming up?
That I don't know. Okay, I mean, there's now you're asking me about things that I don't understand very well. Their notion of the Hitchin vibration is a variant in their situation of something that appears in Nigaud's proof of the fundamental lemma. So they're borrowing ideas from Nigaud. what Ngo's motivation was for his Hitchin fibration and what Hitchin's fibration for his Hitchin fibration were are I don't have an answer to that.
But somehow in that Gross-Zagier thing, they use this relative trace formula kind of thing, right? Orbital integrals and
Yeah, that paper is all about starting from Jacquet's proof of Waldes-Forget's theorem using
yes.
the relative trace formula and upgrading the entire proof to the level of Shtukas. This is different. This looks nothing like that. There's no relative trace formula here. Just like in their Gross-Zagier proof, there's no Eisenstein series at all. It never appears. The proofs have very different flavors, even though they have a lot of commonalities, of course. Yeah.
Thanks. Further questions, comments? If not, let's thank the speaker.
Thank you.